again, now from our example here, now you'll realize that from a given force and a given mass, we can obviously now find our acceleration. So that's the most obvious thing that we can get. So A is F net, no? Divide by mass. And we have that in our earlier problem. So therefore, this is 60 newtons divide by, no, 40 kilograms. No? And with this, no, we can therefore, no, once we know the acceleration, then we can, no, find, no, the other things that are required there. So is the acceleration the one that we are actually looking for? Is that the main question of the problem? Is the acceleration the one that we are trying to find first and foremost? Yes or no?
No, sir.
No.
No, sir.
So that's not the one that we are looking for, but we need that value to be able to find these two other things that we want to determine. So obviously now that value is how much? 1 point how much?
1.5.
1.5,
1.5, sir.
and the unit will be meter per second square. No? And once we know the acceleration to be positive, no, so we realize that the body there is increasing its speed, no. So we will eventually, now once we know acceleration, then the first thing that we can solve, no, the first unknown, no, or first item to locate is the VF value. So final velocity should be VI, no, plus 80. And again, now we recall our equations early on sa atong rectilinear motion, and we realize that they are kind of connected. No? So if the body started from rest, no, and that's our assumption probably, otherwise we will not be able to find this. No? So we will assume. No? So those are things that needs to be implied in the problem, although it's not mentioned. No? We will assume that V sub I is equal to 0. No? Without that assumption, we will have a lacking value here. No? So we will have a missing given. So that will be 0 plus 1.5 times time. Is time given? So we have 6 now. And our VF value is, therefore, how much is our V sub F?
9.
9.
9 meters per second.
So that's 9 meters per second because that's merely velocity. No? So this is a body that is accelerating. So once we know the final velocity, do we need the final velocity to find the distance there? So usually we call
Yes.
distance as S, correct? So S can be solved by V sub I, no? T plus 1/2 AT square. So actually we will not need the final velocity, no? In this, if this is our equation that we are going to use, no? But actually there are two equations that we can actually use, no? If we know the final and the initial velocity, no? So what's the other equation? If we will not use this, what's the other applicable equation? You can also use S to be equal to what? VF square, no? Minus VI square divided by 2A. And we expect that this one will render or give the same answer as the one that we have above, no? Although this is a different expression, but we believe that they should end up with the same answer. No? So this is squared quantities. No? So but for simplicity, since it's much easier to use the first one, so if this value is, if the initial velocity is 0, then our value there will be 0. No? So what is left is actually this one. No? So this is just equals to 1/2 of A, no? Which is 1.5. And then we multiply it with 6 square, no? Okay, then what's our answer there? So again, 6 being squared,
27.
again,
27, sir.
27.
27 meters, no? So again, now since we have an MKS unit there, no? So don't forget that this must be a squared value, no? Okay, so again, now you can try this one and hopefully, no, it will not disagree with our answer, which is 27. No? Let's kind of check the answers that we have here above. No? Hopefully we have a solution there. So there's no solution. Okay. So our answer is basically the same. No? Okay. So did you get the values there? Do you have a question?
Yes, sir. No
Okay.
question.
So here is another problem. No? So from the diagram below, find the tension in the string. So tension is a problem now that is, or a tension is a kind of a force that is pulling the object. No, that's another word for pulling the object. No? So if you push or press the body, that's compression. But if you stretch, no, that's what we call tension or tensile force. No? So it's always outward. No? The direction of tension indicated by letter T is always outward. No? So let me erase this. So we'll have a cleaner figure there. No? So can you note down this problem? And no, I want you to think about how to solve this. No? So can you please note down? So there's a box here that is sliding on a table. The mass of the box is 7 kilograms. There's a string that goes around a pulley. And of course, the pulley now will have the strings there. And it will be subjected to two kinds of tension. No? Now, I think at the bottom of the other end of the pulley, there's another box below, which is 4 kilograms. So what's the tendency of this object, guys? This one will move to the right, or will it move, or will remain steady? So
Remain, sir.
definitely,
Remain steady.
if this one will remain steady, it's a possibility. No? So since this is 7 kilograms, but again, if you have a frictionless table, the table offers no friction at all, that this one will obviously move to the right. No? It will go right. Now, this one will go down, no? By virtue of gravity. No? So there's no other direction for this object but go down. No? Since we are not pulling this to the left, no, this one will not go up. No? So, however, what we will realize is that the acceleration A1 of our box M1 here will be the same in value to the box that goes downward. So the accelerations A1 and A2, since they are connected by a string, will be the same in value. No? So A1 and A2 will be equal in value. No? But what about our tension? Can we consider the tensions T sub 1 and T sub 2 to be the same?
No, sir.
Yes or no?
No,
Why no?
because M1 is heavier, sir.
Because, again,
M1 is heavier.
okay, M1 is heavier, so therefore the tensions will not be the same. No? Now again, if this is what? Now we can call this as a frictionless pulley. No? The pulley does not offer any friction to the string there. We will realize that the tensions here will be obviously the same. No? Okay, they are one system. No? Isa sila ka system, isa sila kahigot. No? We did not tie this string to this pulley. It's free to slide. No? So therefore, the tensions T1 and T2 should be equal in value, but somehow they are kind of opposite in direction. No? Okay, so one thing that we'll realize here is that tensions 1 and tensions 2 must be the same. No? Now, our mass are different, so therefore the weight 1 and weight number 2 are also different. No? Ano ganing equation natin sa weight, guys? Weight
Times gravity.
mass times gravity. So kung ang gravity diri 9.8 times 7, this has a bigger weight compared to the weight on this end. Okay, this one has a smaller mass, no? Assuming that the acceleration due to gravity will be considered at 9.8, no? So one will be of higher weight and this one will be of lesser weight. Now, our body here, na ang iya weight sini will be directed in this manner, no? Dara na yung pakadto, iya weight, no? So this is your weight 1, no? I'll call that weight 1, no? And how much is weight 1? It's M1 multiplied by gravity, no? Our weight sub 2 is also downward, no? If you'll notice it, no? Okay, now what's the question of the problem, gani? What is the problem asking? We want to find the tension on the strings, no? T1 and T2, and we want also to find the acceleration on the strings. However, it's almost 8:30, guys, no? And I have to prepare. I just want you to study this item, this number. Huh? So please learn this. I will check the attendance. So for the time being,